MQTT is a lightweight messaging protocol designed for low bandwidth, high latency applications, and it's quite popular in machine-to-machine or Internet of Things networks. In 1999, Andy Stanford Clark from IBM and Arlen Nipper from Eurotech Inc. created a simple messaging protocol that allowed battery-powered devices connected to oil pipelines to send messages to satellites about the health of the pipeline. At the time, IBM had a set of MQ series software products that helped pass messages on a distributed system. The MQ stood for message queue, so IBM tacked MQ to the front of the name to create the MQ telemetry transport, even though MQTT does not really use queues. In 2013, IBM handed MQTT maintenance over to the nonprofit Organization for the Advancement of Structured Information Standards, or OASIS. Since then, OASIS refers to MQTT as Message Queuing Telemetry Transport. MQTT starts with the broker, which is a service that runs on a central computer somewhere on the network or even the wider internet. The system is designed around a publish-subscribe messaging scheme, also called pub-sub. Clients, which can be any networked device like a computer or a Wi-Fi-enabled microcontroller, connect to the broker over TCP/IP. They can publish to one or more topics, which means sending data to the broker. A topic is a string pattern that the broker uses to filter messages for the connected clients. You can think of topics like directories that hold data or a chat room channel. Clients can also subscribe to topics, which means that they tell the broker which filtered messages they want to hear. When new data is published from any client on a particular topic, the broker relays that message to any of the clients subscribed to that topic. The persistent TCP/IP connections among the clients and broker allow this to happen efficiently with little overhead. Let's take a moment to talk about topic structure. Topics are divided into one or more subtopics by the use of a forward slash in the topic string. Unlike tags, where messages could contain multiple overlapping tags, topics in MQTT are organized in a hierarchical fashion, much like directories in an operating system. For example, in a home automation setup, you might divide your topics into particular buildings or rooms, like home/kitchen/temperature would refer to the temperature data coming from the set of sensors in your kitchen. A few quick notes about topic syntax. You might come across a leading forward slash in some examples to denote a root topic, like you would find the root directory in Unix systems. While this is technically allowed, it's considered bad practice, as it actually creates a topic before the first slash with 0 characters, which can cause some confusion without any added benefit. Also, while any characters in the UTF-8 set are allowed, you should generally stick to the more limited ASCII set for readability, as some clients might not be able to display all the special UTF-8 characters. Again, spaces are allowed, but generally discouraged, as they can lead to ambiguity in reading the different topic levels. And some clients might not encode or decode topic strings with spaces correctly. You'll also see the $ used as a prefix to indicate broker information, such as $sys for getting information like number of clients connected and uptime. So it's often a good idea to avoid the $ in topic names. When it comes to topic subscriptions, you should be aware of the 2 wildcard characters, the +sign and the hash symbol. The +sign indicates a single level wildcard used to mean any one topic or subtopic. For example, home/kitchen/plus means you'd like to subscribe to all of the data collected for the kitchen. It also works in the middle of the hierarchy too. So home/plus/temperature means that you're subscribing to all of the temperature data posted for any room in home. The hash or pound symbol is a multi-level wildcard that can only be used at the end of a topic string. For example, you might subscribe to home/hash to receive data updates for all rooms and all sensors. This matches to any and all subtopics like kitchen, as well as kitchen/temperature and kitchen/humidity. Something to note here is that brokers do not store information from the clients beyond a few exceptions, which we'll talk about later. They simply act as an intermediary to pass information back and forth among the clients. If you want to view a history of your data so you can look for patterns, you usually need to connect some kind of storage mechanism to your broker. In many cases, this is a database like Postgres or MySQL. You'd have an application act as a bridge that connects to the broker as a client and subscribes to whichever topics you'd like to save. Often, this is all of them. As the application gets data from the broker, it saves them to the database. You can then create interfaces to that database to help users analyze the data. This can be something like a graphical dashboard that plots certain topic data points over time. It might be a machine learning model that intelligently looks for patterns to alert users of, say, anomalies. Or maybe you have some kind of automation that reacts to the information. For example, adjusting the thermostat based on aggregated temperature data. Each client has a unique client ID to identify it to the broker. This is a UTF-8 string of up to 256 characters. Like with topics, it's recommended that you stick to the more limited ASCII set for easier displaying and readability. You'll often see these with a prefix of the sensor name or purpose, like kitchen temp, a dash or underscore separator followed by a random set of characters or part of the client's MAC address to create a unique ID. With our network example built, let's talk about a few important features in MQTT. The first is quality of service, or QoS. This is a simple number, 0, 1, or 2, that determines how messages are delivered and affects the reliability and performance of those messages. Level 0 is the lowest level, denoting that a message may be received at most once. A message is sent out once, and the receiver does not acknowledge receipt of the message, which means if the connection is lost and message dropped, it will not be resent. This is also known as fire and forget. It has the lowest overhead, and it's good for situations where some data loss is acceptable, such as periodic sensor readings where another value may come along soon after. QoS1 is the next level, and it stands for at least once. Here, the message is guaranteed to be delivered at least once to the receiver. The receiver must send a packet back to the sender acknowledging receipt of the message. If the sender does not see that acknowledgement in a certain amount of time, it will resend the message and keep doing so until receipt is verified. As a result, multiple duplicate messages may be sent out and possibly received. It adds a little extra overhead but guarantees delivery. This is good for cases when the message is critical but can be received multiple times, such as some types of sensor data or control messages to, say, turn the lights on. Finally, we have QoS2. Here, each message is guaranteed to be received once and only once. It uses a four-way handshake so that both the sender and the receiver know that the message has been received exactly once. These extra packets create overhead on the TCP connection, which can slow down communication between clients and the broker. As a result, QoS2 is best saved for critical messages where duplication might cause issues, such as industrial control sensor data or telling a servo to move in a direction, say, by 2 degrees. QoS 1 and 2 also offer benefits in unreliable networks. Brokers and clients can remember session details so that if a disconnection event happens during message transmission, they will store QoS 1 and 2 messages that were not delivered. When the connection is reestablished using that persistent session, those messages will be sent out again to guarantee delivery. Clients can disable this persistent session by setting the clean session flag to true when connecting to a broker. Note that clients can publish and subscribe at different QoS levels. Publish quality of service determines how messages are sent to the broker, and subscribe quality of service determines how messages are sent from the broker to the client. The broker handles subscriptions independently, which means you can have clients that subscribe at different QoS levels. So you might have one client that publishes a message at QoS 2, which guarantees delivery exactly once to the broker. You might then have a different client subscribe to that topic at QoS 1, which means the broker will guarantee delivery to that client at least once. Yet another client might subscribe at QoS 0 to the same topic, which means the broker will fire and forget messages to that client on that topic with no guarantee of delivery. Another useful feature of MQTT is the ability for a broker to store retained messages. A client can mark a published message as retained. The broker will store this as the retained message for that particular topic, and any clients that connect later and subscribe to that topic will be sent this message. Guaranteed delivery is, of course, dependent on the subscriber's QoS level for that topic. Note that a topic can only have one retained message at a time. Anytime a new retained message for a topic is published, it overwrites the previous one. Let's say your kitchen temperature sensor takes a reading and publishes 23 degrees as the current temperature. It marks this message as retained, so the broker will store this message in the home/kitchen/temperature topic. 15 minutes later, it publishes 24 degrees, also marked as retained. The broker will replace the original 23 with the new 24 as its retained message for that topic. A few minutes later, a new client connects to the broker and subscribes to the home/kitchen/temperature topic. The broker will immediately send this client the latest retained message for that topic, which is 24. Note that no date or timestamp is added to the message, so it's up to the publishing client to add such data, if it's important. Otherwise, new clients will not know when the retained message was originally collected and sent to the broker. Retained messages are incredibly useful to help clients immediately get information from a topic without having to query the publisher through the broker or wait for another update, which might be minutes, hours, or even days away. The last notable feature is the last will and testament, or LWT message. A client can set its LWT message when it connects to a broker, and the broker will store that message so long as the client stays connected. The message is essentially the same as any other published message. It contains a topic, quality of service level, retained message flag, and a payload. The key here is that it's not sent out right away to topic subscribers. Instead, the broker holds on to the message and only sends it out if the client disconnects unexpectedly. If the client sends a proper disconnect message, then the broker simply discards the LWT message. But if the broker detects that the client has disconnected for any other reason, such as a network failure, or the client has crashed, it will send the LWT message to all subscribers of that topic. This is useful for situations where you want to monitor the state of an IoT device. For devices that periodically wake up to collect data and publish to a broker, you can easily monitor if they are connected, disconnected, or have experienced some error. You could also set up tools to, say, automatically notify an administrator that something is wrong, either in the network or client devices. This is a powerful feature that helps you keep an eye on the health of your IoT devices, even in unreliable networks. MQTT is a flexible protocol in that you can use just about anything you'd like for your payload. Here are some of the most common payload types you'll come across. The first is simple plain text. This might be a number or a simple string command like on or off. You can also add a delimiter like a comma to create a simple comma-separated values list. JSON is also very common, as it's an easy, readable way to encode key value pairs in an MQTT message. It's popular because you can include arrays and multiple values in a single message. While not as common as JSON, you'll sometimes come across XML payloads, as data can be tagged similar to the key value pairs in JSON. Finally, the payload can be binary data. This is useful for sending some raw sensor data like compressed images or sound files. You can even use it to send firmware in over-the-air or OTA updates to devices. Up till now, we've been looking at MQTT version 3.1.1, which has been in use since 2014. Oasis released a new spec in 2019 for version 5. Fun fact, there is no version 4. As the version field in the header of the MQTT Connect packet is set to 4 with specification 3.1.1. So to avoid further confusion, version 5 of the specification should now align with this header field. Version 5 introduces a few changes that you should be aware of. One of the first set of notable features is message and session expiry. If the message expiry value is set, messages that aren't delivered in a particular time window are simply dropped, which helps prevent brokers from constantly trying to resend needless QoS 1 and 2 messages or sending outdated values to clients that reconnect after some time. Session expiry allows brokers to keep session information about a client for some time if that client drops unexpectedly. This can include information like subscriptions and unacknowledged messages for QoS 1 and 2. It can be useful when clients are connected through unreliable networks and can be expected to disconnect and reconnect periodically. MQTT 5 also introduces user properties, which are custom key value pairs that can be added to the headers of MQTT messages. Such properties allow customizations to brokers to process messages more efficiently. Shared subscriptions were also added to help with load balancing in large IoT networks. A shared subscription topic is denoted by the first topic set to $share, the group name after that followed by the actual topics. Clients that subscribe to the same shared topic become part of a group as designated by the group name. When the broker sends out data on that topic, it does so to only one client in that group, which can be chosen randomly or part of some scheme like round robin. This is useful for letting just one client in a group perform any required processing of the data while keeping network usage low. While you could build a request-response pattern like you'd find in most HTTP applications out of MQTT messages, it was fairly clunky to do so. MQTT 5 adds a few special fields to some messages to make this process easier. Notably, it adds a response topic field to publish packets. If filled out by a client, the broker still forwards this message to subscribers as before. Receiving clients can look at this field and process the request as desired. They can then publish data as requested. The correlation data field was also added so that the requester can add a unique identifier. The responder can use this same identifier in the correlation data field of the published message, which the original requester can then read to determine that the request was handled, and not just some data that was to be published anyway. Version 5 also introduced a content type field in the message header to allow clients to parse the payload more easily. This is often set to the common MIME types like application/JSON or image/PNG. MQTT 5 adds some other features to help with error handling and scalability, but these are the important ones that you might come across. There is some backwards compatibility between versions 5 and 3.1.1, but I wouldn't count on it. Most modern brokers can handle both 3.1.1 and 5, which means they can handle a mix of version 3.1.1 and 5 clients. That being said, it's always good to check the version compatibility of your broker and client software. Before we finish, we should talk about security. Just like with any network infrastructure, there are a number of ways you can increase the security of your MQTT setup. I'll give you a few basic ones that have a big impact. The first is to set up some authentication for clients, even with a basic username and password. Most brokers support this out of the box. Clients must provide the correct username and password to connect to the broker. The glaring issue here is that both the username and password are sent in plain text over TCP/IP, which means someone could just sniff the traffic to obtain both. To combat this, I always advise configuring transport layer security, or TLS, for anything beyond a simple test MQTT setup. This involves setting up your broker with properly signed certificates. TLS will encrypt messages, including username and password, and prevent man-in-the-middle attacks. You can even take it a step further and enable mutual TLS, where the client and broker must both present valid, trusted certificates to authenticate each other. It's also helpful to configure access control lists to allow only approved clients and specify which topics clients can publish or subscribe to. You can also limit message rate and size to mitigate potential denial of service attacks where one or more clients simply flood the network with packets or large payloads. As usual, keeping all of your software and firmware up to date, along with regular security audits, can help a lot. While there is no limit to the number of security measures you can take, these are some basic steps that you can employ to get started. MQTT is a robust and lightweight protocol specifically designed for IoT applications. Its publish-subscribe model makes it easy to distribute real-time data to all nodes in a network. It's also highly scalable, making it great for everything from small home automation projects to large professional IoT deployments. If you are considering starting such a project, I highly recommend giving MQTT a shot. If you enjoyed this video or found it useful, please like and subscribe. I also recommend checking out my other courses and video series on seanhemel.com/courses. I cover a variety of embedded topics such as Internet of Things, Edge AI, FPGAs, real-time operating systems, and PCB layout. Each of these will give you a great head start in that area if you're looking to level up your programming and hardware skills.